Welcome to Young Prof Academy. Today we are going to be discussing oxidation numbers, balancing of redox reactions, as well as identifying oxidants and reductants in a chemical equation of a reaction. And now I want us to first of all talk about something very important, which is chemical equations of a reaction. Now, a chemical equation of a reaction is of two types. We have the molecular equation of a reaction and we have the ionic equation of a reaction. For example, a molecular equation of a reaction is, let's say we have a salt and let's say we have a sodium hydroxide base reacting with HCl, both in aqueous solution to form sodium chloride aqueous plus H2O liquid. Now here we have what is called a molecular equation. Now let's talk about ionic equation. This molecular equation, before I talk about ionic equation, I want you to understand that a molecular equation only shows you the molecular formula of the compounds or the molecules of elements that are involved in the chemical reaction. It will not tell you how they interact, not show you how the interactions exist. Now, but now look at ionic equation. And using this as an example, I will show you what an ionic equation looks like. Sodium ion aqueous plus hydroxide ion aqueous plus hydrogen ion aqueous plus chloride ion aqueous to give you sodium ion aqueous plus chloride ion aqueous plus H2O. Now here we have our ionic equation. Now I want you to understand that ionic equation shows you the ions that are involved in chemical reaction and how they interact and the interactions that they have. And mind you, I want you to understand that ionic equation tends to have what is called ions that react in both sides of the equation, which we call the spectator ions. For example, in this case, we have sodium and chloride ion in this product side, and we have sodium and chloride ion in this product. These are called the spectator ions. They will now have what is called the net ionic equation when you substitute the spectator ions out. Once you substitute it out, you have hydrogen ion plus hydroxide ion to give you water molecule. So this is the net ionic equation. So now, this will now bring us to what we have on the board, which is oxidation number. And oxidation number is just like simply oxidation number is the valency or the combining power of an element, because oxidation number is as a result of either a gain or loss of an electron during a chemical reaction. And we all know that metals ionizes by electron gain and non-metals ionizes by electron loss. For example, let us say we are asked to calculate for oxidation number of a particular element in a compound. I want you to understand that there are rules that guide us in naming or in identifying the oxidation number that is attributed to a particular element or compound. Which one of the rules involve that oxygen is always -2, but -1 in peroxide and -0.5 in superoxide. The algebraic sum of the oxidation number of a compound is equal to 0, while as the algebraic sum of the oxidation number of a radical is equal to the charge of the radical. Same thing with the oxidation number of an ion is the charge that it has. And the oxidation number of a neutral element is equal to 0. And we all know, same as the rules, in the rules that all group 1 elements have oxidation number of +1, all group 2 elements have oxidation number of +2, and also all group 3 elements has oxidation number of +3, while the latter numbers might have 5, and so group 7 is -1, as the case might be. Now, because we are writing WAEC and JAMB, our scope of concentration will be towards those, because those of element of group 1 and group 2. And in this case, you are going to be having, let's say you are asked to find the oxidation number of, look at this, find example, find the oxidation number of sulfur in H2XO4, let's say carbon in CaCO3, let's say magnesium in magnesium oxide. Let's say I have to give I have to give example from a radical. Let me check. Let's use more example from radicals. Let's say, for example, let's say you're asked to find the oscillation number of manganese in MnO4. Just want to be specific. Manganese in MnO4 minus, something like this. Or let's say uh, chromium in K2Cr2O72 minus, something of this nature. We have to calculate the oscillation number. It's very easy. You just have to apply the rules. Once you apply the rules, you get your answer. Okay, we are going to be doing it now. Take your time, write it down. Okay, I'm going to clean the board now so we can solve this problem. Okay, maybe I should write it here. Sulfur in H2XO4, calcium in Caco3, magnesium in MgO, manganese in MnO4 minus, and Cr, that's chromium, in K2Cr2O72 minus. Now, very easy to solve. You might see something like this in your JAM examination 2026 on your WEC 26, and this is how you approach it. Now, for this, let's start with number one. Let's start with number one. Sulfur in H2SO4. Sulfur in H2XO4. Now, it's very easy to solve once you know the rules and apply it. Now, if you look at this, we are already told that the oxidation number of a compound is equal to zero. That's the sum of the algebraic sum of oxidation number of a compound is equal to zero. So what you have to do now is you say oxidation number of hydrogen plus oxidation number of sulfur plus oxidation number of oxygen is equal to zero. And mind you, hydrogen is existing as a diatomic molecule here, and oxygen is existing as a tetraatomic molecule here. So in this case, what you have to do is that is 2 in bracket oxidation number of hydrogen, and hydrogen belongs to group 1, which tells you that the oxidation number of hydrogen is plus 1. So 1 plus oxidation number of sulfur is what we are looking for. Let us call it X plus this 4. Oxidation number of oxygen, which is always minus 2, in, or less in hydroxide, which is minus 1, and superoxide, which is minus half, is equal to 0. So when you solve this arithmetic, you have 2 plus 2 times 1 is 2 plus x plus 4 times minus 2, which is minus 8, minus cancelled plus minus 8 equal to 0. So therefore 2 plus x is equal to 0 plus 8, which is 8. Therefore x, which is what we're looking for, is equal to, if these two crossing sign of equality, becomes 8 minus 2. X is equal to 6. Now I want you to know that with the identification of, or the calculation of the oxidation number of this sulfur, you can be able to name this particular inorganic compound. Very easy. Now, if you look at this, this is tetra, 4. Just like we say mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, as the case might be. So in this case, this is tetra oxo sulfate. What's sulfate now? Sulfate 6 in Roman numeral. Acid, because of the presence of hydrogen is an acid. So this is how you get it done. For number 2, now I'm going to leave you to solve this. Send me your answer in your comment section. Then same thing with this. Then I'm going to solve this. Then I leave you to solve this. So I'm going to solve this and this. Why you solve this, and leave me your answer in your comment section. So for this, we have oxidation number of potassium plus oxidation number of chromium plus oxidation number of oxygen equal to the algebraic sum of the oxidation number of a compound or a radical is equal to the charge it carries also minus 2. So in this case, you're going to be having now potassium belongs to group 1 element, or rather group 2. If I'm not mistaken, potassium, calcium. If you look at the periodic table, potassium should be group 2 element. Or rather, okay, let me to to check it. It's very easy to do. Just have to hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, which is group 1 element. Like I said, potassium is group 1 element. So in this case, I think this will be useful to us when we start doing periodic table as well as trends and the properties of periodic table. So in this case, if I want to solve for potassium, I'm going to clean this now, which is 1 element. The oxidation number is 1. So this would be like, since it is existing as a diatomic molecule, I'll say 2 brackets 1 plus oxidation number of chromium, which I'll call, and if you notice the chromium is existing as a diatomic element 2, so plus 2 bracket x, which is what we're looking for, the oxidation number of chromium, plus, and if you look at the oxygen here, it is heptatomic 7, as polyatomic, it's 7 bracket, oxygen is always minus 2, say minus 2 is equal to minus 2, which is the algebraic sum of the oxidation number of a radical is equal to the charge that the radical has. So in this case, we have 2 plus 2x. 7 times minus 2 is minus 14. So in this case, minus plus is minus 14 is equal to minus 2. So when you do the arithmetic and of this nature of 2 plus 2x is equal to minus 2 plus 14, which is 2 plus 2x is equal to 14 minus 2, which is 12. And in this case now, 2 plus 2x is equal to 2, or you can say 2x is equal to 12 minus 2, which is equal to 2x is equal to 10. Definitely divide both sides by 2, x is equal to 5. So in this case, this compound can be named as potassium heptaoxochromate 5 ion. So that's the name, potassium heptaoxochromate 5 ion. If you look at it now, you notice that since this guy is having potassium 2, if you exchange radicals, potassium 2 heptaoxochromate 5 ion. So that is the name of this compound. So with this, you can solve any problem that is involved in oxidation number in your examination. So now we are going to balance